I can hear you out there thinking, what about non-conservative forces? Can we try an example problem that uses non-conservative forces with conservation of energy? We can and we shall, right now. We've got a helicopter hovering at an altitude of 1 kilometer above the ground when a panel from its underside breaks loose and plummets. Let's draw a diagram of that panel. Oh man, what a panel. The mass is 15 kilograms. 15 kilograms. Oh buddy. It starts from rest, we'll say, at this state 0. I'll label this state 0. And the height here will be that 1 kilometer or 1,000 meters. And that's above the ground. Then it plummets and it hits the ground with a speed of 45 meters per second. So down here at some later time, at some y1 that we'll call 0, we will now have some final velocity here, v1, that will be 45 meters per second. Okay, and this was that kilometer above that it started. Now the question is, how much mechanical energy was dissipated by air resistance during our panel's descent? Well, we can write a conservation of energy statement, and we'll just include that non-conservative force of aerodynamic drag and solve for it. So mechanical energy is not conserved, but overall energy is still conserved. It just goes into aerodynamic drag. That means we can say that E naught plus whatever work is done by drag on our system, we expect this to do negative work as it slows down our system, is equal to E1. I'll write this out as 1/2 mv naught squared plus mg y naught plus the work of drag is equal to 1/2 mv1 squared plus mg y1. Let's zero out the things that we know are 0 to simplify our lives. And rewrite this, now solving for the work of drag. All we have to do is move mg y naught to the other side, and we will have our work of drag being equal to 1/2 mv1 squared minus mg y naught. This is it. We're done. We have to plug in numbers. We will do that. 1/2 mass of 15 kilograms times velocity, finally, of 45 meters per second squared minus same mass, 15 kilograms, times gravity of 9.8 meters per second squared times y naught of 1,000 meters. Lovely. Plug that in, we get an answer of the work of drag here is negative 130 kilojoules. That means that drag has done negative 130 kilojoules of work on our system, or it's dissipated 130 kilojoules worth of energy. So I could say, if I'm answering how much mechanical energy was dissipated, 130 kilojoules of energy, of mechanical energy was dissipated. Dissipated. Box it and end the problem.